started the meeting. Let me go to people. Okay. 1 more minute and then we can get going. I see we have some attendees from yesterday's fish banks presentation. So there's some attendees from basically the free learning lab or learning hub that the South African Systems Dynamics chapter hosts, which is very heartwarming to see. Okay, so I just want to change the status of some people very, very quickly here. Right. Just so that they can speak. All right, so welcome everybody to the very first seminar hosted by the South African System Dynamics chapter. Before we get into our seminar, I'd just like to give everybody a little bit more information about our South African System Dynamics chapter. And I see it's great. Everybody is recording their names, where they're from, which country, which affiliation they're with. So the South African System Dynamics chapter runs a series of seminars. Generally, we run 3 seminars a year. And for 2026, our seminar presenter for today is Dr. Ivan Taylor, and his topic is Systems Engineering Perspective on Reducing Impact Without Escalation or Wishful Thinking. So Dr. Ivan has presented numerous times at our conference that's hosted annually by the South African System Dynamics chapter. So we are familiar with him, and I can guarantee this is going to be an excellent presentation based on all of the other presentations he's made. So in terms of the chapter, who are we? We are a chapter of volunteers. I've got some of the members online, so if you guys can just unmute, say hello, show yourselves. There you go. There's a wave from Andres, from Malaysia, Rudolph's online as well. So those are some of our chapter members. We are affiliated to the International System Dynamics Society, and we were officially recognized at the 2014 Winter Policy Meeting held by the International System Dynamics Society. So our vision, of course, we do want to be globally recognized, and I think we've got to that point. I actually forgot to introduce myself. So to those people that don't know me, I'm Nalini Pillay. So I'm the immediate past president of the South African System Dynamics chapter and a founding member. Andries Botha, Dr. Andries, that's online as well. He's the current president of the chapter. And there he is, on and off like a flash. And so I do have a full-time job. I work as a corporate specialist, specializing in system dynamics modeling for an electricity utility in South Africa. No guesses there. I think people might figure out which company that is, but very proud to be part of that company. It's been an amazing, gosh, 30 odd years. So, in terms of the vision for the South African System Dynamics chapter, we do want to be globally recognized and a leading chapter as far as system dynamics is concerned. Our aim when we first started was really to advance skills in Africa. However, we have gone further and we have actually reached out to the international community and found that we can support the international society to improve and develop skills in systems thinking and system dynamics modeling, which we then have been doing. In terms of our mission, of course, is to grow system dynamic skills and capabilities through a bunch of efforts. And one of those is the free seminars that we offer because we believe, a lot of people are students, and as students, you don't have a lot of pocket money. So we try and make sure that a lot of our events are free and accessible. So that's me. That's now the outgoing president, Dr. Andres. We have Professor Rudolph, who's also online, Dr. Young, who does a fabulous job at our YouTube channel. And then we have a lazy who I think, I think will be completely lost without because she does a little bit of everything in the chapter, but a lot of LinkedIn marketing and all of our posts and so on. So she's absolutely fantastic, as is the rest of our team. So in terms of upcoming events, just very quickly, we are busy right now today with seminar one. We do have more seminars coming up. You can access them via our website, and someone will post the link to the website on the chat. We also have what we call the Learning Hub. And the Learning Hub is where we have 3 streams for beginner modelers, or even if you're not a beginner modeler. I also attended and I also learned a bunch of stuff, even though I've been modeling since 2010. You always learn something. So people are welcome to be part of it. We have a sponsor, which is IC Systems, and we have Karim from there who has supported this free initiative over several years. It is facilitated this year by Dr. Andres and completely free to enter, completely free in terms of the support that you get and access to IC Stellar Architect, which you can use during the duration of the competition. You get one-on-one guidance throughout, and when you're done with that particular stream, you are welcome to join the subsequent streams. Stream 4, that's for our advanced modelers. And then just a reminder that we have our 14th South African System Dynamics chapter hosted conference from the 19th to the 20th of November this year. So please, this year it's free as well. So we are hoping, and it's online, so we're hoping to get as many people as possible. Last year we had excellent presentations. It was just absolutely fantastic. So we do hope to see everybody there. Remember, at no cost online, so you don't incur any other expenses. So please do join us. Now, in terms of how you can be connected with our chapter, we have a whole lot of links, and I saw Lazy's already posting a whole bunch of them. But getting back to why we're here, I'll just tell you a little bit more about Dr. Ivan. Dr. Ivan is a senior researcher and applied scientist with more than 4 decades of experience in system dynamics, in systems engineering, in operational research, and public policy analysis. He is president of Policy Dynamics Incorporated and a scientist emeritus at Defense Research and Development Canada, where his work has supported decision-making across infrastructure, healthcare, cybersecurity, energy, and social systems. Dr. Taylor has an extensive record of peer-reviewed publications and applied modeling projects, and he has held leadership roles within the International Council on Systems Engineering, also known as INCOSE, as well as the System Dynamics Society. His current work focuses on integrating life cycle, socio-technical, and sustainability considerations into rigorous systems engineering practice. So from here, I'm going to stop sharing and allow Ivan to share and take us through his presentation. Ivan, over to you.
Hey, thanks, Anili, for that presentation. Please speak up, Anili, if my voice goes soft. Sometimes my voice doesn't come through very well, but
I'll
I'll try
let
to
you
speak
know.
up. Um, yeah, so today I'm going to talk about systems engineering, which is a little different from system dynamics. I'm a member of, as Anili said, I'm a member of the International Council on Systems Engineering, which is a large organization of over 25,000 systems engineers around the world. I think we're in 85 countries, and we're trying to extend ourselves into Africa in a bigger way through the INCOSE Foundation. Um, and I'm also a member of the System Dynamics Society. I have been since 1997, and in the System Dynamics Society, I'm a one-on-one mentor. And so, if you're interested in getting mentoring for maybe a year or so on a weekly basis, that's what I do for the System Dynamics Society. And anyways, so this work is work I've been doing with Orte Andrek Para Valencia of Colombia. And what I'm doing is I'm trying to bring together some of the ideas that we're learning in the Systems Engineering Society's working groups, particularly the Natural Systems Working Group and the Social Systems Working Group, to help with building sustainable systems. So my title of my talk is Systems Engineering Perspective on Reducing Impact Without Escalation and or Wishful Thinking. And I think that, we all know in system dynamics that structure determines behavior. And so what I want to emphasize today is design and builds the structure, and that then, of course, leads to the long-term behavior. So the purpose of the presentation is to position sustainability as a systems property, not as a program or add-on, to demonstrate what systems engineers can learn from natural systems and indigenous societies, and to show how the INCOSE, International Council on Systems Engineering's working groups are influencing mainstream systems engineering practice, and connect these ideas explicitly to the systems engineering life cycle. So the goal is that we want to build sustainability into our systems. So in framing the problem, I think we all know that despite decades of sustainability initiatives, the impacts continue to accumulate. And this is not a motivational failure, it's a design failure. Systems behave exactly as they are designed to behave, and late-stage fixes cannot compensate for early design decisions. So, this emphasizes that, bad outcomes reflect structural problems in systems. So, as I said, I'm going to be talking about the work we're doing to translate knowledge from the area of natural systems into systems engineering. And I think what we can learn from natural systems is how to build durable systems and how natural systems adapt to their environment. So why natural systems matter to systems engineering? Well, natural systems have persisted for billions of years, and they operate within hard physical and ecological limits. They protect slow changing stocks such as soil, water, biodiversity, and climate. They evolve through feedback, not centralized control. And collapse occurs when limits are violated. So we need to respect the limits of systems, and we need to recognize feedback in those systems. So key properties of long-lived natural systems is that there's clear boundaries between the system and the environment, strong coupling between actions and consequences, preference for resilience over short-term efficiency, redundancy and diversity as design features, and there's no externalization of risk or waste. So we see that the durability of natural systems comes from their resilience and their adaptability. Now I'm going to talk about indigenous societies, which we're studying in the social systems working group, and how we can learn from them to build more sustainable systems. And the primary thing we can learn from indigenous societies is the idea of stewardship. So indigenous societies as a sustainable socio-technical systems, many indigenous societies have persisted for centuries in the same ecosystems. Sustainability is embedded in governance and not treated as a separate objective. Decisions account for long time horizons and future generations. Resource use is constrained by cultural rules and responsibilities, and social norms enforce limits long before physical scarcity appears. So indigenous societies use governance to sustain systems over long time horizons. So what can systems engineers learn from indigenous practice? Governance is part of system architecture. Values and responsibilities shape behavior as much as technology. Long-term feedback must be visible and respected. Accountability cannot be deferred to future actors. And sustainability is enforced structurally, not rhetorically. So here we again see that governance shapes the system's outcomes. So now I'm going to talk about the INCOSE working groups that shape the ideas entering into systems engineering practice. So there's 54 working groups in INCOSE, maybe more now, and they cover a large number of specialized areas of systems engineering. So I'm going to talk about a few of them today that I've been working with, but there's many more that are also important. So why working groups matter? They act as innovation engines for the International Council on Systems Engineering, and they translate emerging thinking into the systems engineering body of knowledge, which is the state of the art of systems engineering. And it's a wiki document that's available on the web. It's open source, and it's forward facing. So we use that to explain to other people and to use as a repository for ourselves about the state of the art of systems engineering. And primarily what it does is it concentrates on the literature that's available and directs people to appropriate literature in various fields of systems engineering. And then we influence future editions of the Systems Engineering Handbook. And the Systems Engineering Handbook is the state of the practice of systems engineering. And then we shape how new systems engineers are trained. And the way systems engineers are trained in INCOSE is through a certification process. So they have a very detailed and effective certification process in INCOSE, and that involves studying and writing an exam on the information in the systems engineering handbook. So you have to demonstrate your knowledge of the state of the practice of systems engineering, and that's a great feature of INCOSE, is this ability to certify systems engineers. And working groups do a lot to shape that in terms of helping to contribute to the systems engineering handbook. So the first working group I'm going to talk about is the natural systems working group, and this brings ecological thinking into systems engineering practice. It highlights limits, carrying capacity, and slow changing variables. It encourages engineers to model environmental systems explicitly, and it promotes learning from ecosystems as reference systems. So, it helps to spread. It uses ecology to inform systems engineering choices, and it spreads information to other systems engineers about natural systems and how they work and how they can help in engineering decision making. And then the next working group is the adaptability working group, and they recognize that sustainability requires the ability to adapt over long life cycles, and that many sustainability failures stem from brittle designs, and that it needs to focus on uncertainty, change, and surprise by design, and it emphasizes governed adaptation, not ad hoc fixes. So adaptability obviously supports sustainability. The next working group that I'm going to talk about is the social systems working group, and it focuses on human behavior, institutions, and governance. It addresses policy resistance and unintended consequence. It integrates social feedback into technical system models, and it emphasizes co-evolution of technology and society. So social structures matter as well. And then there's the sustainability working group itself, which raises awareness of sustainability in systems engineering. It supports integration of environmental, social, and economic considerations. It promotes sustainability-oriented design practices. It develops resources and publications on sustainability in systems engineering, and it builds capacity in members and society. And so what the sustainability working group is trying to translate sustainability into systems engineering practice. Okay, so now I'm going to talk about the systems engineering life cycle and sustainability. And what we need to do is we need to embed in sustainability thinking across the 8 phases of the systems engineering life cycle. And I'll go into each of these phases individually. And this is a big part of the systems engineering practice. So the first phase is conceptualization, where we define the system purpose beyond short-term performance. We identify protected stocks and unacceptable losses. We establish system boundaries in terms of social and natural systems, and we make long-term impacts explicit from the start. So the idea here is that we need to recognize that these early choices made in the conceptualization phase have very long-term outcomes. And then we move into the requirements phase, which translates sustainability concerns into enforceable constraints. It tries to avoid vague or aspirational sustainability statements. It specifies limits, thresholds, and responsibilities. And a big thing is that it ensures traceability to long-term system behavior. So the requirements phase is a place where we make a priority of sustainability in real systems. Then we can move to the architecture phase, where we define systems boundaries, interfaces, and external dependencies. We lock in material, energy, and information. We decide what is inside and what is pushed outside. We shape coupling between technical, social, and natural systems, and we constrain future behavior through irreversible structural choices. So architecture is the structure that leads to the future behavior. And then we move into the design phase, which translates the architecture into detailed mechanisms and controls. And design feedback makes impacts visible and timely. We embed monitoring, reporting, and accountability mechanisms. We prevent displacement of impacts outside the system boundary. And we favor robustness and resilience over fragile optimization. So this is where we turn intentions into mechanisms. And this is where we do so-called trade studies, which involve possibly things like digital twins and system dynamics to look at the behavior of the system once it's developed. The next phase is integration and test phase, which puts together the system and reveals the emergent behavior created by interacting components. And we test sustainability-related behavior, and we identify coupling, delays, and feedback missed in design. We stress test the system against boundary conditions and uncertainty, and we detect escalation risks before deployment. So here we're looking at the interactions, and you can expose hidden problems in the design of the system. So the next phase is verification and validation, where we test the system behavior under stress and not just nominal conditions. We validate long-term impacts, not only short-term performance. We ensure sustainability requirements are actually enforceable, and we check for unintended consequences and policy resistance. So here we're testing system behavior of the system under pressure. But another aspect of it is that we're tracing all of these ideas of these tests back to requirements and conceptualization. So we need to have traceability from right throughout the whole system development, so that everything is coordinated and testable and relates back to original requirements. The next phase is operations and evolution phase, where we monitor the slow changing stocks, not only the fast performance metrics. We embed feedback loops into operational governance. We adjust rules, incentives, and controls. And then we treat adaptation and learning as normal operational functions. And operations is where sustainability actually is found. And systems evolution can help with sustainability. Finally, we have decommissioning and disposal phase. We plan the end-of-life behavior at the beginning of the life cycle. We define responsibilities for residual impacts and long-living systems. We prevent cost and risk transfer to future generations. We design for dismantling, reuse, and material recovery. We treat disposal as a system behavior, not a cleanup. And planning, here we want to make sure that we're planning for end of life, and that needs to start very early in the design process. So now I'm going to go through a few examples of ways that these kind of ideas have been implemented. These examples are meant to show recurring patterns in systems engineering that lead to sustainability. They're not perfect, but they do indicate, where we can make changes in our designs. It also recognizes that these changes must be built into the system. So the first one is interface carpet tiles. And here we have a product called modular commercial carpet tiles. And we designed the architecture here for circular recovery. Modularity turns waste into managed flow. So here we have modularity as a design feature, and this enables recovery of material. Oh, by the way, I should mention that, INCOSE has no necessarily connection to these, except that these are examples of what we think are good design practices. The second example is Pagonia repairable clothing. And here, the product is outdoor apparel designed for repair and reuse. And the company has embedded repair and reuse into the system. And here they make governance, make sustainability operational. So Patagonia has shown that repair can be operationalized and organizational structures can support it. The next example is the Fairphone modular smartphone. And here we have a modular smartphone designed for repairability. And the company has made sure that they design for repair, not replacement. And the message here is that if repair is hard, the architecture has failed. And that's a message that I'll be making throughout the conclusion of this presentation. The next example is Philips Lighting as a Service. And here the product is lighting provided as a service rather than as equipment sale. And this changes the incentives by changing the ownership. And we have service models that reward durability and recovery. So here, the incentives have created by ownership reshape the design logic. The next one is Nordson Precision Agriculture Systems. And the product is sensor-based agricultural management systems. And this makes environmental feedback visible for better sensing, which provides better decision-making. And here we can see that better feedback can make better management possible. And this can be used to protect soil and water to make it work better for long term. The next one is the DNV offshore wind lifecycle design. And the product here is large-scale offshore wind turbines. And the company can make longer life technically possible by using engineering assessments that support safe continued operation. So here they design the system to be able to extend the life as long as possible. Okay, my closing thoughts are that natural systems and indigenous societies show what works. INCOSE's working groups provide the translation mechanism to translate these ideas into systems engineering practice. And we have the opportunity to design and redesign systems so that sustainability is unavoidable. And I think that's the message that I want to make, is that we want to make sustainability unavoidable with our designs. So some key messages for systems engineers is that sustainability emerges from structure, not intent. If sustainable behavior is easy, the design is flawed, which again, I think strength is basically the message I'm trying to make, is that unsustainable behavior must be designed out of the system. And then systems engineering already has the tools it needs. The challenge is how and when to apply them. And then the final message for system dynamicists is that sustainability is a dynamic outcome of system structure. And so that is basically our continuing message that structure determines behavior, and that persistent unsustainable behavior signals misaligned feedbacks, delays, and decision rules. So that shows how system dynamics can be used in these processes. System dynamics provides the concepts and methods to reveal these patterns, and the real task is to identify high leverage interventions that prevent harm without creating new problems. And as a system dynamicist first and a systems engineer second, I found that INCOSE is very friendly to system dynamics. They're very oriented towards thinking the way system dynamicists think, and they want to see system dynamics applied to their systems more and more. So they're very happy to see system dynamicists in their society. Okay, thank you for your time and attention, and I'll open the floor for questions and comments. You can reach me at these email addresses at my INCOSE.net accounts, myself and Orte.
Great. Thanks a lot, Dr. Ivan. I think we've picked up a fair amount of how we can connect the INCOSE space with the systems engineering aspects to system dynamics and that fraternity. So there's a couple of questions that we have in the chat. The first one is from Dr. Andres. Andres, you can unmute and ask your questions. I think I have provided that.
I mean, the first question is basically, what would you estimate is the extent of system dynamics applications in systems engineering? Is it visible, or is it still, knocking at the door?
Yeah, I think it's probably still knocking at the door. I think a lot of people are very interested in applying systems engineering, but they don't necessarily have the skills themselves. So I think there's a real opportunity for system dynamicists to enter into this field and provide services to the systems engineers to help them with their design processes. One of the things that I think the systems engineers would really appreciate is the idea of digital twins to help them foresee the impacts of their design decisions. So in the design phase, there's these things called trade studies, and these trade studies could really benefit from the idea of digital twins. And then the digital twins can also show how the structure and the design affects the long-term behavior. So I think there's a lot of scope for system dynamics in systems engineering. And like I said, I've been very welcomed into the society, and they're very interested in my work. I've given presentations at their international symposium. I have a presentation coming up in June at their international symposium on system dynamics and circular design. And I've given presentations at their international workshop. And so and even though there's a very small number of people in the organization who practice system dynamics, I think there's a lot of interest in it.
Right. Thank you for that.
Yes.
I see, Andres, you had a second question.
Yes. So one of my conundrums is, when is it an unintended consequence, a true unintended consequence? Or when is it just a really bad design decision? How do you distinguish between the two?
Yeah, that's a very good point. Is that I guess the fact that it's unintended implies that it is a bad design decision. So that the people didn't foresee the consequences when they made the design. So I think those two ideas are probably inseparable, as you say, that if you designed it properly, you wouldn't have those unintended consequences. I guess the other idea is, that there is a possibility that there are positive unintended consequences, but in general, unintended consequences tend to be perceived as negative. Anyways, so yeah, I agree with you completely that unintended consequences really stem from poor design choices.
Okay, great. Thank you, Andres, for those
Sorry, Nalini,
questions.
if I can just
Yes.
comment on that, Ivan,
Yeah,
I
yeah.
think one of the best examples of positive unintended consequence is the use of system dynamics and releasing wolves back into the Yellowstone Park. There's a nice video on YouTube if you bother to find it to see that. But that is really, there's the natural stuff we all expected, but then there's this much bigger changes in the system that nobody anticipated, even in the simulations. That has been extremely positive in that. So just if anybody is interested, just have a hand for that YouTube video. It's worth watching.
Thank you. Thank you for that.
All right, great. Then we've also got a question from Alesi. Alesi, you're most welcome to unmute and ask your question.
Yes, I don't know if you can hear me well.
Yes.
Yes. Okay. Thank you, Dr. Ivan, for the presentation. I was wondering actually, like nowadays, the term sustainability has assumed many definitions. So at the same time that you brought a few examples that I think that translated to sustainability in a certain way, I wonder how you or how from a systems engineering perspective, you can work with this loose definition of sustainability and how do you translate it into systems requirements? Thank you.
Yeah, that's a great question as well. Systems engineering, at least the working groups that I'm in part of, spend an exorbitant amount of time discussing definitions, and they need to be very clear about what they mean when they say something, and that's where we need to recognize how that this shows up in requirements. So when systems engineers are building a system, they have to come up with requirements, and those requirements are intended to be unambiguous and traceable. So, for example, the requirements are traced to the stakeholder needs, and then the system design is traceable to the requirements, and then you have tests and evaluations that test that the system design is actually meeting the requirements. So when it comes to sustainability, I think definitely the definitions of it are very loose. There's many definitions of sustainability and many different points of view on it. But when it comes to actually the engineering of systems, it comes down to the requirements that are specified in building the system, and those have to be clear and unambiguous, or the system just won't work properly and won't be able to be validated. So yeah, so I think they work around the fuzziness of sustainability by making them clear in the requirements phase.
All right. Alesi, you happy with that? I see she's nodding, so thank you. Yes, the session would not be complete without a question from Prof. Rudolph. Go for it.
Yes, there you are. Yeah, I think this is an important topic, but I think one of the things that us as system engineers will still struggle, I'm also part of a COSI, and we are part of the Complex Systems Working Group, which is related to this, and we've just started a new systems thinking working group. which some couple of times in the meeting, system dynamics have been mentioned already. So I don't know if you're aware of that group, but I think I've been struggling a very long time in identifying how and where to apply system dynamics as part of systems engineering. And I think one of the starting points is you have to ask the right questions. You can't just go and model your system the same way as you typically will approach a MBSE type architecture type modeling. I think you have to ask a question and you answer the question with your model. Any comments on how to train or guide systems engineers to ask the right questions of us?
Yeah, that's a great question. It's a question about questions, but yeah, I think the idea is to try to get systems engineers to look at the long term. So when they need to be looking past the immediate requirements, the immediate needs of the users, and into the longer term extensions of the life and the end of life decisions and the long term behavior of the system. So I think that may be a way to get systems engineers to think about asking the right questions. And I think system dynamics tends to do that. It tends to look at long-term impacts. So, often system dynamics models will look at systems, 20, 30, 40, 50 years into the future and how those systems will develop and adapt. And I think that's where maybe systems engineering might need to expand its viewpoint to these longer term decisions.
Yeah, thanks. I
Right.
agree.
Great. So I have a question before we get back to Andres. So you always end up sometimes with some executive management or some leaders who say, listen, we want something simple, an approach that doesn't have much complexity, something that's quick to deliver on. They look at this entire systems engineering approach to getting a sustainable solution out, and they say, for real world delivery, this is not going to work for us. So how do you actually bring them on board? How can you how do you respond to them? What's your strategy?
Yeah, yeah, that's a very, very good point as well. That definitely there's value in parsimony, and there's value in keeping things simple. Um, but but often you can't avoid the complexity in the real world, and um, I think it's a challenge for us to balance complexity and simplicity. And I think there is a fair amount of pushback from non-systems engineers, especially in management, to the constraints of systems engineering. So, for example, systems engineering is sort of a methodical process of going through conceptualization, requirements, architecture, design, test and validation, and a lot of managers and project leaders just want to get going, get it done, and they believe in, say, uh, agility and prototyping to prove their point, rather than doing the whole design and development process in a methodical way. And that's not a problem. I think that's to some extent that's a good thing. However, I think we should make sure that we're being careful to ensure that we are meeting the requirements that are specified by the system and the users. without necessarily like we were talking about, without unintended consequences. So yeah, as I said, there's a very good book which you might be aware of, and it's called How Big Things Get Done, and it's making its way around the systems engineering organizations, and it's primarily about project management, but it's primarily about a lot of case studies that were done on major architectural activities, and it describes some rules that can be used to have successful large systems, and and then it also describes a lot of case studies of designs that actually were not well done, and it tries to learn from those examples. So I think that, with small systems, I think it's easy to be simple. But as the systems get larger, it's more likely that they'll become more complex.
Okay, all right. Just from our experience, with having developed and founded a system dynamics center within an electricity utility, which is also quite odd in itself, for us to get executive support, we actually latched onto one of the flagship projects and developed a model that made a lot of the qualitative aspects quantitative, and then we presented that in a way that they immediately saw the benefit. So we used something sort of as bait to sell the skill. And after that, there was just like, listen, just build us a center with engineers who can do this fun stuff. So I think you need to, if you get the strategy right, you're probably halfway there already. Andres has another question.
Lily,
Can you
maybe I
be,
can,
yes, you can
yeah,
go
I
for
can
it.
maybe also add to what you're saying. Is my experience is first you need to build trust, and then you win them with pretty. And the solid engineering you keep for the engineers. So the accuracy and the good stuff, the kind of stuff I'm interested in, you keep for the engineers, and you let people who can do the pretty, and make the executives feel warm and fuzzy. So I had a session this morning where that happened. But my question to you, Ivan, is you made a statement that I think it's something like sustainable solutions versus fragile optimization. Can you maybe elaborate a bit on that?
Yeah, yeah, that comes from a little bit from my exposure to operations research in my career, where they focus primarily on optimization and primarily constrained optimization. However, sometimes highly optimized systems are are unstable to small changes. So that's where I think the idea of robustness is important, and I think systems engineers understand robustness, and they build in, different uh, uh, safety measures so that it can handle stresses beyond the norm, and and so yeah, so I think that that you can't expect systems to do everything, but you need to make sure they cover a large range of possible situations that they could face. So robustness is a big part of systems engineering, and making sure that systems can handle things that are maybe outside the original scope of the design.
Okay, all
Thank you.
right, great. We'll just take the last question and then we'll close the session. So the last comment with a question is from Rudri. A lot of systems are already set up and are not working well in terms of sustainability. So how can systems engineering help with improving the design of the system so that sustainability becomes inherent, especially when it's not possible or difficult to create a new system?
Yeah, that's a great question as well. Yeah, I think that definitely redesign of systems is difficult once they've been put in place, and having having inappropriate structures that lead to bad results and sustainability is the issue. I think the primary focus that I might have is to look at governance and incentives. So, there must be incentives in the system that are set up to lead to unsustainable behavior. And maybe if you can affect those incentives to lead to more sustainable behavior, you might be able to help redesign the system.
Okay, all right, great. I think that's it for the session today. Can I ask if people, whoever can, just turn your camera on? With online session, we still like to kind of show the society and everybody else that, we are actually supporting skills development and also get some publicity through that. So whoever can, turn your cameras on so we can do a screenshot. Kareem, Shale, Rudri. There's Rudri. I saw your name yesterday in the workshop. Olga, Mrs. Burrow. Okay, great. Let's do a screenshot. Everyone ready? Smile. You get this. Yeah. I'm going to drop it in the chat. So if you guys want to take it from the chat before you leave, you're most welcome to as well. And thank you all for joining us with the session. Thank you, Dr. Ivan. We really appreciate your time. We definitely got some insights from that. So I hope everyone will join us for the next seminar, and we'll keep everybody informed in terms of email communication, or just please check out for a lazy posting through our South African System Dynamics LinkedIn page. Thank you, everybody. Have a lovely evening, morning, wherever you are connecting from. Bye.
Bye.